So let's do an example of a position graph and try and interpret what its velocity graph is, and then do a velocity graph and try and interpret what its position graph is. So let's just suppose I have a position graph describing some motion here, and I've got, let's say it starts at 0. Oh, sorry, get my axes labeled. It starts at 0, and it rises like that for a certain time, and then it does that, and then it does that again, and then it does that. Okay, and so we want to qualitatively describe that. We can plug in numbers later. Let's qualitatively describe that. What would its velocity graph look like? Okay, and I'm going to be careful here, or I'm going to reveal that we have to be a little careful with our values by having both positive and negative available for my velocity. So with this position versus time curve, can we describe what the velocity versus time curve is going to be? First of all, this length right here, it's constant, it's uniform motion here, so we should expect a constant value on our velocity graph. It is rising, it's positive x versus time, which means I should have a positive value on my velocity. So I can, for the first time here, I can have some positive value there. Okay, these tick marks here would indicate these times. Okay. Alright, what about the next one? Here's a constant speed, but a slope of 0. There's no rise over this non-zero run. Excuse me. So the slope of 0 means I have a value of 0. So between this time interval, we have a value of 0. Okay. Now I've chosen not a very realistic time. This means it's moving and instantaneously stopped. Okay, which doesn't really happen, but to emphasize the relationship between velocity and position without talking about acceleration yet, we're just going to pretend that is a real motion. But it does often cause a question to occur of what happens here. This is a value here, and then suddenly it's not. What happens at that point? And you can either leave it blank there, do dots to indicate it's a transition, or you can even do a solid line that's purely vertical. Again, in real life, there would be some curves to that as it's transitioning through a very real acceleration. This gives us an infinite acceleration, which is not real. But again, we'll hold to this model to emphasize just the relationship between velocity and position, and leave acceleration for another time. Okay, so if that's the case, we have a positive slope here, giving us a positive value here that's constant in both cases. A 0 slope, okay, which gives us a 0 value here, and then we have a positive constant slope again, and it appears to be about the same slope, the same rise over the same run as the first leg, so it should come back up to about here, and I'll go ahead and do that connecting part here. Okay, so it should be about the same size, same value here because it's the same slope here. Now we get to this last slope. Okay, over a small time interval, about half the time interval, it drops twice as far. So this went up some amount, went up about the same amount, but now it drops both those amounts, or the total amount, in half the time. So we have a fall. That means we're going to be in a negative value of velocity. It's a negative slope, and it is 4 times steeper than this rise. This rise, let's say this was 1 unit tall over 1 unit in time. Okay, this would be 2 units of fall over half a unit of time. And so we would end up with a velocity that's 4 times bigger but negative. So over this small interval here, trying to draw about 4 times, we have this value here for that short amount of time. And we don't know what happens after that. Okay, so we have this negative velocity is 4 times the value. Okay. Now let's go ahead and get some numbers in here just to make it a little bit more concrete. We have it qualitatively described. This is about 4 times, but negative. These two are about the same value. Okay, let's get some numbers in here. Let's say this is 1 second, 2 seconds, 3 seconds, and that's going to be 3.5 seconds. Okay, let's say this is 1 meter and 2 meters. Okay, so what would be the velocity values here? Okay, so with our definition, we can have our delta, our v equals our delta x over delta t. We can choose here's 0 for a starting point. So for the first leg, okay, so for the first leg, we're going to get a rise of 1 meter minus 0, okay, over 1 second minus 0, gives us a velocity of 1 meter per second. So this is a value of 1, okay, with units of meters per second. Alright, I guess I should be careful here. This is units of meters. This is the units of seconds, units of seconds. Okay, now in the second case, we have a rise of 0, though we have a run of 1 second. Okay, so in the second case, we have our final is 1 minus the initial, which was 1, over 2 minus 1, so that still gives us 0. Okay, in the third case, we have a final is now at 2 meters, so 2 meters minus our initial point of that section was 1 meter, and our time was 3 seconds minus 2 seconds. Okay, so our final time over original time for this portion of the uniform motion, and so that's still going to be a rise of 1 over a run of 1, which gives us our 1 meters per second. So even though it was higher up and further along, it's the slope that matters, not where it's at. So we get the same value here. Then that last leg, our final position is 0 minus our initial position was 2. Okay. Our final time is 3.5 minus 3. Okay, and so this gives us a 1 or 0.5 or 1/2 in the denominator, okay, and a -2 up top, which flipping that denominator around, putting the 2 in the numerator, gives us the -4. So if I were to draw that mark there, that'd be -4. Okay, so we've now been able to look at our graphs and do the math to see how the slope is what matters in determining the value of our velocity, the slope of a position versus time graph.